All right, today we are cracking open a fascinating ecological detective story. I mean, this is a case file that took 100 years to solve. The victim? A tree. The crime scene? We're talking about an entire subcontinent. And the culprit? Well, the culprit was a master of disguise.
So this is really the central question that just haunted scientists for generations. Think about it. We're not talking about a few sick trees here and there. This was a catastrophic landscape-level collapse. So how does something so huge, so vital, just start dying?
Okay, so let's get into it. Meet our victim, the Shisham tree. Now, this isn't just any old tree. It's an absolute economic powerhouse. We're talking about the premier hardwood for a billion-dollar timber industry. And it's also an ecological anchor. Its roots fix nitrogen right into the soil, which helps stabilize these really fragile ecosystems. And just look at this devastating map. The crime scene is massive. It's like a heat map of death stretching all across the Punjab, with mortality rates hitting a staggering 70 to 80% along canal sides. The stakes? They couldn't be any higher.
So, like any good investigation, the first thing scientists had to do was get down to the crime scene and start examining the evidence. They had to figure out exactly what they were looking at to try and profile the killer's method.
Now, this is where it gets really interesting. Kind of like a coroner's report for a tree. The first clues were right there for everyone to see. The attack started at the top, a slow, progressive death of branches moving downward, creating this grim skeletal crown that they called stag-headedness. Then the trunk itself would start showing these desperate signs of a struggle, splitting bark, sap just bleeding out everywhere. And if you peeled back that bark, you'd see these bluish-gray streaks staining the whole vascular system, a clear sign of a fatal blockage. And finally, underground, completely out of sight, the root network was just rotting away, cutting off the tree's lifeline.
But this right here, this is where the investigation hit a massive roadblock, one that stalled everything for decades. You see, investigators couldn't even agree on what to call it. Was this dieback or was it wilt? They look similar, but they're fundamentally different things. Dieback is this slow, top-down killer with that bluish stain. Wilt, on the other hand, is a super-fast bottom-up collapse and has a pinkish stain. This one critical misdiagnosis sent a century of research down dozens and dozens of the wrong paths.
And yeah, because of all that confusion, this thing did not get solved quickly. It basically became one of forest pathology's great cold cases, a century-long investigation, just filled with false leads and dead ends.
And this timeline just shows you how twisted the whole investigation got. The case officially kicks off way back in 1918, with a root rot fungus as the first suspect. It was plausible, but totally wrong. Then, from the 50s through the 70s, the entire focus shifted to something called Fusarium solani, the fungus that actually causes wilt. Even as late as the year 2000, a huge outbreak was incorrectly blamed on a water mold. It really wasn't until after 2010, when scientists were armed with modern DNA tools, that they finally pinned down the true culprit behind dieback, Ceratocystis delbriganicans.
And this quote from the source material, man, it just says it all. The constant arguing, the conflicting theories, it didn't just slow things down. For the better part of 100 years, it actively stopped progress in its tracks. The whole investigation was basically stuck on a loop. But then there was a breakthrough. The kind of plot twist you always hope for in a great detective story. Researchers realized they'd been looking for a single culprit this whole time, like a lone gunman. But the truth? Well, the truth was way more complex and a whole lot more systemic.
And this just illustrates the first part of that breakthrough perfectly. Turns out, we humans were basically accessories to the crime. We had built a perfect transmission highway for this disease. See, for decades, the common practice was to plant genetic clones, all identical, in these dense rows. It's called a monoculture. And this had two devastating effects. First, zero genetic diversity meant that if one tree was vulnerable, they were all vulnerable. And second, and this is the crazy part, their root systems literally fused together underground, creating this invisible super spreader network for the pathogen to just zip from tree to tree.
Right, so the next piece of evidence came from the genetic forensics lab. DNA analysis showed that the killer wasn't a single thing at all. It was a shapeshifter, constantly mutating and evolving on its own in different regions. You can see it clearly on this slide. These genetic trees show that the fungus from one area was completely different from one just a few miles away. And that meant there was no magic bullet. A chemical that worked in one district would be totally useless in the next. The enemy was a moving target.
Okay, so we've got a man-made disease highway and a shape-shifting enemy.
But does that really explain the sheer scale of the devastation? I mean, was it really just an aggressive fungus? Or was there something even bigger at play here?
And here's the answer. The case wasn't solved by finding one culprit. It was solved by understanding that it was a total systemic failure, a perfect storm that's represented by this Shisham disease triangle. You needed all three sides for the disaster to happen. First, you needed a vulnerable host, those genetically identical trees we planted. Second, an aggressive pathogen, the diverse, rapidly evolving fungi. And third, the real catalyst, the environment, planting trees in waterlogged, oxygen-starved soils that basically suffocated their natural defenses. It took all three working together to create this mass mortality event.
So, with all the evidence in, we can finally give this case a proper definition. Shisham dieback isn't just a disease, it's an ecological reaction. It's the predictable, tragic result you get when decades of mismanaged forestry practices collide head-on with an incredibly clever and adaptable pathogen.
So, case closed on the why. But the story doesn't stop there, right? Solving the crime is just the first step. Now the question becomes, how do we get justice for the victim? How do we actually engineer a recovery for an entire ecosystem?
Incredibly, the key to the future was hiding in plain sight the whole time. Researchers went out into these devastated forests and they started studying the survivors, the healthy trees still standing in the middle of all the death. And they discovered these survivors all shared distinct physical blueprints. You can see it here. The resistant trees had this compact, almost umbrella-like shape with branches pointing downward, while the susceptible trees had that more typical upward growth. Nature had already figured out the solution. We just had to learn how to read its blueprints.
So the second part of the solution was to re-engineer the crime scene itself. On the left, you've got the problem, what they call the canal bank trap, where that waterlogged soil just suffocates the roots, making them easy prey. And on the right, you see this elegant solution, an agroforestry model. It's where trees are planted on these elevated mounds. This simple change in the landscape drains away the stagnant water, letting the roots breathe and actually defend themselves.
So you put all that together and the path to restoration becomes crystal clear. First, you have to abolish the monocultures. That means using seeds only from those proven field-tested survivor trees. Second, you need intelligent site matching. No more planting in those high-risk waterlogged areas, period. And third, management has to become localized. You have to fight a diverse pathogen with a genetically diverse army of trees.
And here it is, the complete recovery protocol. It's a comprehensive checklist, really, built on a century of painful lessons. It starts with proper diagnosis and sanitation. Then it moves to immediate actions, like applying biological agents to help the healthy trees that are left. And then it focuses on the long game, engineering the right soil conditions, and, most importantly, replanting with the right, resistant Shisham trees in the right places.
So, the 100-year mystery of the dying Shisham is finally solved. But the real lesson was never just about one tree. It's about a whole new way of thinking, about seeing the entire system, not just the symptom. Which leaves us with a final and pretty crucial question. Can we apply this systemic blueprint to protect our planet's other vital keystone species before they become the next cold case?